The next result that we are going to discuss is called the alternating series test, right? There it says when you have an alternating series. Let's take an example. Let's take this one, the sigma of -1 to the power n 1 over n, right? Now this representation says that it will give you plus and minus signs interchangeably, right? That is, one after the other you will get plus and minus signs, and it really doesn't matter, like for the alternating series test to work, it really doesn't matter whether they have mentioned this one as -1 to the power n minus 1, or even if it is to the power n, the same result will hold true, right? And so in the example that I wrote, I have mentioned that interchanging property of 1 and -1 as to the power n, right? And here in the original statement you have n minus 1, and the difference is when you write it like this one, so that means when you substitute n equals 1, you will get -1 for the very first term. But in this case, when you substitute 1, you will have -1 to the power 0. So you will have plus 1 as the very first term. So if you need to have plus 1 in the beginning, you should write this one. And if you need to have -1 in the beginning, you should write this one. And even you can write -1 to the power n plus 1 if you need to get plus 1 in the beginning, right? So all these things will give the, like, it doesn't matter which representation that you have used for the -1 to the power n term, right? Okay, so having said that, in this particular series we can visualize it as sigma -1 to the power n bn, where bn is equal to the sequence of 1 over n. That's what we have here, right? I will delete all these markings so it is easy for you to see. Right, here we have it. So now in this particular example, bn represents 1 over n, because that's how they have written down the original series, right? And now this alternating series test says that if you have these two conditions, then the alternating series converges, and this doesn't say anything about divergence. Okay, so it's like if the series is alternating and if these two conditions are satisfied, then the series will converge, and if they do not satisfy, we cannot say anything about the convergence. So we can only make a conclusion if these two things are satisfied for a given alternating series, right? Otherwise the alternating series test will not be helpful. Okay, so it doesn't say anything like if they do not satisfy the condition, if a given series do not satisfy these conditions, we cannot directly say that the series diverges. Okay, if it doesn't satisfy any of these conditions, we cannot say that the series diverge, or we cannot say it converge, right? So in that case the alternating series test will fail. Okay, right. Now, but in this case you can see that bn plus 1 is always greater than bn. So this is our bn, and bn plus 1 will be equal to n plus 1. See, here the denominator is larger than this one, so this total answer will be greater than this one, because the denominator of this one is greater. So bn plus 1 will be less than or equal to bn, right? Even if it has a strict inequality, that doesn't matter, right? Remember, I said 5 is equal to 5 is a true statement, and you can even write it as 5 greater than or equal to 5. This is also a true statement because this is included in here, but you cannot write 5 greater than 5. Okay, similarly 5 less than 6 is a true statement. 5 less than or equal to 6 is also a true statement, but you cannot write 5 equal to 6. Okay, this is a false statement, right? And now we have this condition satisfied for the given series. And how about the other one? Is this true? Limit bn n goes to infinity. So that means limit, now here when you are taking the limit, we are not considering this negative 1 to the power n term. Okay, we are only taking the bn terms. And also, before going into that, you should see now here in the alternating series test, this bn sequence should be a positive sequence, right? It cannot have negative numbers because all the negative numbers are there inside this one, right? So bn itself is a positive sequence. Okay, keep that also in your mind, right? Now here that property is also satisfied for the bn that we chose, right? And for that one you can see that the limit is equal to 0. So this condition is also satisfied. Now that means we have an alternating series. Why do we call it as an alternating series? The plus and minus signs will interchange one after the other. So we have an alternating series, and we extracted out the bn, which is a positive which is a positive sequence, and for that sequence it has both these conditions. The decreasing nature, this is called the decreasing nature, because when n goes to a larger value, the sequence points will decrease and the limit is equal to 0, right? So the series converges from the alternating series test. And now here also we are not discussing the proof of this theorem, right? It's like I am not telling you the reason for why this holds true, right? We are just directly using the result to evaluate the convergence of given series. Now let's consider this example, right? So you can see that it is an alternating series because of this term, right? Therefore bn will be equal to this one. And instead of checking this one, first let's see about this condition, whether that is true. So for that one we will need the limit of bn, which is equal to the limit of 3n over 4n minus 1, right? And that will be equal to 3 over 4, right? So it is not equal to 1. In other words, this condition is not satisfied by this equation, right? So the limit, the alternating series test cannot be applied for this series, right? In other words, we cannot determine the convergence of this series through the alternating series test. But now you can consider a different test to determine the convergence. So for that, let's consider our series as sigma an. So in that case, our an should be equal to -1 to the power n 3n over 4n minus 1, right? If you consider it like that, right? So consider the limit of an, right? You can see that the limit of an does not exist, right? Just because of this alternating notation, or alternating nature, where you can see it in a different way. Now just suppose if this has only positive terms, right? If the sequence has only positive terms, right? If it has only positive terms like this, then the sequence converge to 3 over 4. And just suppose if it has only negative terms, then like something like this, then it will converge to negative 3 over 4. Okay, so but the thing is, this sequence, when you have plus and minuses interchangeably, that sequence, now here you have 3 over 4 and here you will get negative 3 over 4. So it will oscillate between plus and minus 3 over, is like not in between, but this sequence tries to converge to both this one as well as to negative 3 over 4. Therefore it does not has a common value for this entire sequence to converge, right? So if we go in the positive direction, all those positive terms try to approach positive 3 over 4, and all these negative terms will try to approach negative 3 over 4. But unfortunately within this sequence you have both negative and positive terms, so this entire sequence does not converge to any point. It's like if you just consider the positive terms only, it will go to 3 over 4. If you consider the negative terms only, it will go to negative 3 over 4. But if you consider the entire sequence together with both positive and negative terms, then it does not have a common point to converge. So basically this does not have a limit. But remember, if a series converges, then this limit should be equal to 0. Okay, so in other words we can say if this is not equal to 0, then the series does not converge. So the limit is not equal to 0, then therefore from that divergence test theorem we can say that our series diverges. But now we will try to do the same application for the previous question also. Now there the series that we used was this one, okay, that is sigma negative 1 to the power n 1 over n. So if we consider this as our sequence, okay, that is negative 1 to the power n 1 over n, you can see if you consider the positive terms only, it goes to 0, and even for the negative terms it will again go to 0, right? See here, both positive and negative terms go to a same value. Therefore it does not have any restrictions as it was before in this second problem, right? But of course having this equal to 0 does not guarantee that the corresponding series will converge, okay? But if this is not equal to 0, we know for sure that the corresponding series will diverge, right? Okay, and now in the next video also we will do one more example under alternating series test.